Okay, sorry, because I accidentally stopped the previous video, so that's why I have to start a new part. And let's just continue from what we just stopped in the previous video. So here we have to solve b, okay? And as I said, we take b equal to 3n, okay, which satisfies the first equation, but at the same time we have to guarantee 3n has to be congruent to 3. So that's why we now solve this equation. And of course, n is some integer, okay, for some integer, okay, not just any numbers. Well, for this equation, you can take, okay, we take n equal to 1, then it's satisfied, then it solved the equation, okay. Oh, why? It solved the equation, and we get a equal, okay, sorry, b equal to 3 times 1, which equal to 3. Okay, so here we got the two variables a and b, and now hence we take x equal to a plus b as we discussed before, which is 5 plus 3, which is 8. Then x equal to 8, solve the original system. Okay, so that's how we solve that system, okay, by solving two other simple system. Okay, now of course we are not satisfied with this because maybe I mentioned that already. We want to solve the problem in a more general way, in the sense that we want to get all the solutions. Okay, so here's the question. So how can we find all solutions to the system? Okay, the system I mentioned is this. Okay, how can we get all x which is congruent to 2 modulo 3 and x congruent to 3 modulo 5? So we got one already. Okay, we got one which is x equal to 8. Okay, so actually the answer is pretty simple. Okay, so we claim that. Okay, and maybe you can also make an observation to see the solution. So we claim that, okay, x equal to 8 plus 15, okay, 15m, okay, for m being integer, okay, solves the system. Okay, and all solution. Okay, actually we have two things to check. Okay, so first we need to check whether this solution, so-called solution, x equal to x plus 15m, isn't that solve? I mean, does it solve the original system? Well, you can just plug in and check. It must solve the system. Okay, it must solve the system. But that's not difficult to see that because it's just by direct checking. Now the second part is more challenging because we have to show they are all the solution. That means if we have any other solution, then it must be in the form like x plus 15m for some integer m. Okay, so that is more challenging. How can you guarantee all the solution must be in that form? Okay, so this is the proof. Okay, now of course by direct checking, as I said, by direct checking, this solve the original system. And to see why it gives all the solution. Now, how can you show it gives all the solution? That means if you have any other solution to the problem, to the system, okay, then that solution must be in that form. If you can do that, then you're done. Okay, so let's say, suppose, let me use another letter, z. Okay, z is another solution to the system. Okay, then we have this. Okay, we have z congruent to 8. Okay, which is congruent to 2 modulo 3. Okay, and also z is congruent to 8 congruent to 3 modulo 5. Now why I haven't put that 8, okay, in between the two, the z and the number, because I have to make use of that 8, because as I said, I want to show z has to be in the form like 8 plus 15m, right? Now how can you get that 8? Okay, so that is the reason why we got the 8. Anyway, now, okay, so let me just copy this, and then we move on to the next page maybe. Now this is what we got, because remember we claim, okay, so we assume that z is a solution. Okay, so it's a solution, that means it must congruent to 2 modulo 3 and it must congruent to 3 modulo 5. Okay, this is the reason. Okay, that is the definition for being a solution, right? But on the other hand, we already got one solution, okay, which is 8. So that's why you can put that 8 in between, okay, and you still get the same thing, okay. But now, using that, okay, for example, so let me just call that equation number 1, okay, and let's say this is equation number 2. Now from 2, from 1, okay, we can take z equal to 8 plus 3l, okay, for some, or maybe I use another letter, 3n, for some integer n. Okay, why? Because z is congruent to 8, okay, which is in the congruence modulo 3. So that's why if you take the difference, z minus x must be a multiple of 3. So that's why you can get this expression. Okay. Now, what next? Well, the next thing we can do is to put this z equal to x plus 3n into the second equation. So we put 3 into the second equation. Okay. Then we have this. We have 8 plus 3n, which is congruent to 3. But now, because you're putting that into the second equation, we are not taking congruence with respect to 3. So we have to take congruence with respect to 5. So we got this. And so we have 3n, which is congruent to 0, modulo 5. Okay, because the x just got cancelled. Actually, you see, that x is sort of not that important. Okay, because remember that h is just a particular solution, just one solution. So it shouldn't make it so important at all. Okay. Anyway, now this is more important. Okay, 3n has to be congruent to 0 modulo 5. Okay. Now think about it. How can you get this? Now okay, that means 3n has to be a multiple of 5. That means you get 3n. Okay, so that means, let me just type it, which gives 3n equal to 5l. Okay, for some integer l, of course, for some integer l. Now think about it. If you have numbers n and l, we satisfy that equation, 3n equal to 5l, right? What can you say about n and l? Now, one thing is, one important key for this problem is you have to observe that 3 and 5, they are actually relatively prime. Okay, so they have no common factors at all except 1. Okay, now, but you see, okay, for example, you can see that 3n equal to 5l. Okay, so that means 5l is a multiple of 3. Now, how can it be? How can you get that factor 3 for 5l? If 3 and 5 they are relatively prime, so there's no way you can get that factor 3 from 5, right? So that means that 3 must be coming from the integer l. Okay, that's important. So let me just type it. Okay, since GCD, okay, they can think about it. So GCD of 3 and 5 is equal to 1. So you must get this. You must have n, okay, equal to 5, 5 what? 5 q, okay, for example, for some integer q. Otherwise, how can you can think about it, okay, if it's not the case, how can you make that equation be possible? That means that n must be containing the factor 5, okay, because that 3 cannot keep any factor 5. So in order to make 3n as a multiple of 5, so that n must contains the multiple the factor 5. So that means n equal to 5q for some integer q. Now this is important because now if you put it back to number 3, now see what? So hence by number 3 is this equation, okay? We got this z equal to 8 plus 3, okay, now n is 5q, so you get 5q, okay, which is equal to 8 plus 15q. So, sorry, not x, but z, okay? So that means even though you have any other solution to the problem, z, okay, still, after the analysis there, you can show that z must be equals to 8 plus 15 times some integer q, which is exactly this form. Okay, so you solve the problem. Therefore, z is also in the form 8 plus 15m, m being integer. So 8 plus 15m, m being integer, gives all the possible solutions. Okay, done. So that's why we can show all the solution is in that form. Now, of course, I'm a little bit cheating in the sense that I just give you the answer, but how can you get that 15, right? Where does it? Okay, how can you get 15? In fact, okay, this is a remark, okay? In fact, that 15 is not some mysterious number, okay? That 15 actually comes from LCM of 3 and 5, okay? So that 3 and 5 is exactly coming from the congruence relation, because now we're taking congruence with respect to 3, and for the other equation we are taking congruence with respect to 5. So we have 3 and 5, which is exactly the 3 and 5 in the LCM. In particular, because they're relatively prime to each other, so the LCM is just the product of 3 and 5. So that's why we got 15. Okay? So in general, of course, if we are solving some other problem, okay, you have to understand what's going on. In general, for the system, okay, for example, you have x congruence to capital letter A, for example, modulo m1, and x congruence to b, So in an abstract form, okay. So of course a, b, n1, n2, they are integers, okay. If the GCD of n1 and n2, they're equal to 1, and if x0 is one solution to the system, then the general solution is always given by this. It's given by x equal to x0 plus, okay, m1 m1 times n2 multiplied to m being any integer, okay. So that will always give you the full set of solution, okay. So this is the most general solution to the problem, okay. Now, in fact, the above method is known as Chinese remainder theorem, okay. Now I can say a little bit about the history, why we call that method as Chinese remainder theorem. In fact, this is one type of problem which we can find from the Asian Chinese book, okay, some Asian Chinese books, okay, and that and there is a very long history for that kind of problem. In particular, it just about solving system of linear congruence equation, okay. So from those Asian Chinese books, we can find the method, okay. So that's why we just give the credit to the Asian Chinese. So that's why it's called a Chinese remainder theorem, okay. So if you're interested in the history, I can suggest you to search, okay, just search this Chinese remainder theorem. For example, you go back here, okay, and then click it. Then you can easily see this Chinese remainder theorem, okay. Even the history, you can check it, okay. So it's a long time ago. You can even see that 1,000. Not 1,000. 1,247. Okay, so it's like almost 80. Not 80. 800 years ago. Okay, so it's a long time ago. Okay, and the Asian Chinese already knew the method to solve this kind of linear congruence equation. Okay, so you can check it, okay, by yourself. Okay. Now we know how to solve system of linear congruence equation with two equations, okay. Of course, we are not satisfied with that, okay. And in particular, I'm afraid maybe you still don't quite understand the method behind it, okay. So that's why I will give you examples in solving system of linear congruence equation with three equations. Now you won't see any problem for four equations because actually 4 and 3, there is no big difference, but just more complicated. So I think 3 is enough, okay. So if you understand the way in solving system of linear congruence equation with 3 equation, then I'm pretty sure you understand the method, okay. And the method actually is very similar to the case for 2 equation, but you will see it. You just have to be more, you just have to be very patient and just solve the problem step by step, and then you will get it. Okay, so let me type out the question before the end for this part of video. So for example, now we want to solve this problem x congruent to 2 modulo 3 and x congruent to 3 modulo 5 and x congruent to 2 modulo 7. Okay, so because I'm using the web file in typing those equations, Okay, so that's why I'm a bit silly.